Hi, my name is Cantor. I'm a PhD from Western University. My PhD was in biomedical engineering, and I did a postdoc in collaboration with IBM Research in deep learning.
Hi, my name is Michael Vertolli, and I'm a PhD student at Carleton University. I also study deep learning, and I'm a facilitator today.
Hi, I'm Dave MacDonald. I'm a solution architect at Wrangle, and I help facilitate today.
Today's talk is about a style-based generator architecture in the context of generative adversarial networks. I hope you enjoyed the talk. Okay, so my name is Diego. I'm really happy to be here today. I have a small startup company called Ezra, and our mission is to help people detecting cancer earlier. So far, we're doing it with success. We have a prostate cancer AI that I can tell you is the best in the world so far, until someone comes with something better. Our accuracy is about 93% compared to the state of the art. The other two groups working on this, they have an area under the curve of 93% and the other one 84%. Our area under the curve is 97%. So it's really good. We are tackling a number of problems that are very specific to radiology that you don't have in computer vision. And I don't have free time, of course. So, and my personal project is to bathe and feed myself every day. That's like my goal. Other than that, I'm working. My goal today is to share with you my personal understanding of how this works. So let's get started. So we're going to talk about the generator. Can anyone see, everybody see the slides? Is that okay? Can we see them? Okay, so I don't work with GANs. So this was, I'm familiar with the concept, and this was one of my first exposures to looking into these boxes. And what I realized from the literature is that the generator is usually a network, and there is no way for you to manipulate the examples that are synthesized by this network. So the purpose of the topic today, or the purpose of the research group here, is to provide a way to manipulate very intelligently the function of the generator. So we're going to look into that today. And they are going to do this by sharing from the literature of style transfer. So this is an example, a very basic example of a style transfer network. On one hand, you have your input, this is an image, and then you have a style, there's another image, and then you have an operation here called adaptive input that is going to try to transfer this style to this image, and this is what you see here. So there is an encoding part and there is a decoder part, and you train this by looking at two different types of losses. One is the regular loss that you would see in any network, and on the other hand, you have this style loss. So the idea is to minimize the style loss as well in such a way that you are effectively transferring the style to the input image. So the key to unlock the understanding of how this works is looking at this function, looking at the idea. Everything starts with the batch normalization idea. And I didn't understand what this meant. Like, I read many papers talking about batch normalization, and they always talk about the
covariance shift.
Covariance shift. And I was like, okay, but I don't understand what that means.
That's not after.
So I think that I figured it out. So the idea, we're going to talk about how that works, but the idea here is everything starts from this point. So at some point in research, people started using this. And when they started using this here triggered everything else. Up to today, we were seeing this type of results. So specifically in GANs, they started using batch normalization to improve the discriminator training. This wasn't used initially in the generator. And this is a loss. This is a curve of the loss. This is the style loss that I showed you before. So when you do batch normalization, this works very nicely here. And then the next step was to do it for every instance. So instead of having your batch, calculating the mean and the standard deviation of your batch, and then having the network learning these parameters through backpropagation, you're going to do the same but for every instance. And when you do that for every instance, then the style the network learns better the style. And from previous papers, you have results that look like this. So you have your content image here.
Your fingers blocking.
Sorry. So this is the image and this is the style. When you do batch normalization, for style transfer, you have results that look like this. When you do it for every instance, then you start seeing something that looks, that you would describe as a better transfer of the style. So this is what this looks like, and again here, this is exactly the same plot that I showed you before. Now, the next step, so we went from batch normalization to instant normalization, so the next step, that is the key for this paper, is the adaptive instance normalization. So the idea here is that you have your input, and you're going to have your style. And here is exactly the same operation as before. This doesn't change. You have your input here, you calculate your statistics, your mean and your standard deviation. And then what changes here is that now you're going to shift by the, you're going to multiply by the variance of your style, and you're going to shift by the mean of your style. So if you compare this equation with respect to the other two previous equations, what you're going to realize is that ADA-in doesn't have any learnable parameters. So pay attention to that. Here, the gamma and the beta, and here the gamma and the beta were learned through backpropagation. Here, we do backpropagation, but this operation is totally transparent to backpropagation. There is nothing to learn. This is very important. Also, when you talk about batch normalization, imagine that you have a batch of examples, and there is some kind of variance and some mean in your batch. But you know that that standard variation don't represent the mean and the standard variation of your population or of your universe, right? Sure. So what batch normalization is doing is removing the specific mean and the specific variance of your batch. So you are normalizing, you don't care so much about that. And then through backpropagation, what we're going to try and learn is these two parameters that are specific to, is a good estimation of your population. Right? So basically here in batch normalization, you're removing the abnormal or the spurious variability that you have in the particular sample that you selected. So when you do that consistently and you allow backpropagation to learn these two parameters, then you're effectively finding the correct statistics for your population. So this is my understanding on how backpropagation is useful, and that's why you see that when you use backpropagation, learning happens much more efficiently. Yes.
So in this case, sorry, what exactly is the instance, and how do you?
An instance is just one example. So instead of taking a batch and then calculating, so you calculate this mean and this standard deviation for every element in your batch. So when you do learning, you pass everything. You calculate you pass the batch through the network. And then at the end, you have a batch over which you calculate the loss, right? And then you backpropagate that, load the gradients, and then this is how you start learning these parameters here.
No, I understand that, but
yeah.
I'm just wondering, for instance.
Yes, for instance, one by one.
But how do you calculate mu x for the instance?
So mu x here is over the instance. So you do the mean for every channel of every example.
Okay. So you're talking about RGB channel here?
Yes.
Okay.
So you do it independently for every channel.
Okay.
So it's a similar mechanism as with a batch, but you do it one by one.
So 2 questions. If you move back to the previous slide, please. Okay. So the difference over the last 2 was their normalization against batch norm, right? Is that correct?
So here you are normalizing with respect to the batch.
Yeah.
And here this is the result with instance normalization. So this is batch normalization, this is instance normalization.
Across the channel, right?
You do it for every channel, yes. For every channel of every element of the batch, here you have a batch of 1.
Well, just untitled.
Just one step.
Yeah.
So for each element, there are 3?
Yeah. In this case.
Okay. If you now move forward, please. So how, I'm trying to see the bigger picture. How are these related, these 3 elements?
So, as you see, it's exactly the same mathematical formulation. In these 2 cases, through backpropagation, you're going to learn these statistics. In this particular case, you don't learn anything because this is given by your style.
This is primary.
So this add-in operation is transferring the style, and in the next slide, I'm going to try to explain how it does it. Instead of thinking.
Yeah, I think just want to be clear. So the first equation, you don't have, you say there are no parameters, right?
Here there are no
learnable parameters.
Yeah.
Within here, how you actually came up with y could be learned.
Yeah.
Right? There's just, in this piece of this, there's no learnable parameters.
And in reality, the style is not, that's an input.
Right.
So this
Yes.
is an input as well as the image.
I mean, it's derivative of the forward propagation of your network, right?
But in this operation, there is nothing to be adjusted by backpropagation. Everything is input.
So no matter what stage of training your network is in, that's not going to change?
Exactly. No matter where in training you are, this operation is completely transparent when you backpropagate.
Just that operation.
Just this operation.
Okay. Later on, you're going to explain how they, because I'm still a little bit fuzzy how they intermingle.
Well, let's agree for the moment being that this operation is untouched by backpropagation because you don't have any learnable parameters. That's the big difference between this and these 2.
So the point you're trying to make is if you go instance, you get more sort of intuitive, more refined control.
Yes, it seems to be that when you use, like the previous research, and this is a paper you want to check it, it's in the slides.
Okay.
When you go from a batch normalization to instance normalization, style transfer is finer.
Okay.
And the reason for that is, in my opinion, is because you get better statistics here. Because you have the statistics of the specific style.
Okay.
Right?
Can I ask you a question?
Sure.
So the mu in the next slide, but don't go, no, come back. Because I would like to actually connect these pictures to that mu and then signal.
I'm going to do that. I'm going to do that in the next slide.
Okay.
And if not, then you can tell me.
Sure, yes.
Okay. So, again, so I want to try and hear and understand how this works. So too high there. So say for a second that I would like to transfer. This is not part of the paper. This is just like how I'm working things out in my head. So say that I want to transfer this style into this image. So what would the end result look like to you? So think about it for a second. So here, let's start just with the color channels, right? We said that these operations of style transfer work per channel. So let's simplify the problem and say that here, if you are going to take the histograms of these three channels, you would say that your blue channel histogram is white, and there is a lot of information there, right? And the red and green, probably they would have little information.
Sure.
Right? So let's assume that it's negligible for the segment. And what would be the case for this image if you were going to look at the histograms in the 3 different channels? So same idea, you would imagine that the red channel would look populated, and then the other 2 channels would be insignificant. All right? So let's take the blue channel here. Let's take this image. We said that the other 2 channels is non-significant. So we're going to take this X and imagine for 1 second that this image here is just a distribution of values here, right? We're going to take this X and we're going to subtract the mean. So you have the blue channel and you subtract the mean, then now everything is going to be empty, right? Because there is a lot of it and you don't have any, you remove the blue, right? So you have a lot of blue all over, and then you find the mean blue value, and then you remove it, then it's going to be very, very empty, right? And you do the same with the distribution. So if there's blue, all sorts of blues, like all across, it's a very wide histogram, and you divide by this, then it's going to exactly, then you're going to have very small variation. So this operation is removing the statistics of that particular image. So if the image is a distribution of blues, by doing what is inside the parentheses, you have something that's blank, right? So imagine that, keep that idea in mind. When we normalize, we're losing the specific statistics that we have. In this particular case, we lose the statistics of the image. When you do batch normalization, you remove the specific spurious statistics of your batch, which is what you want because you don't care so much about that. You care about the statistics of the universe. Right? So this kind of makes sense. This is kind of the intuition behind it. Now, this y here, the mu y and the sigma y, are the statistics of the style. This is the style that you want. Right? Oh, sorry, the other way around. So I'm going to transfer
Either way.
this style into that image, right? Because that's how it started, okay?
Sure.
Okay.
Do you know what I'm doing? Because I started this way, but now we're going to do it that way. Make sense? Who doesn't understand? I'll try to do it.
I'm a bit lost.
You good?
I just want to confirm, the mean of x, is that across the channels?
Yes, so we took a dummy example, and we're simplifying it. In this particular case, we have two images, one with information in the blue channel, and the other one with information in the red channel, and we are saying that for the purpose of the analysis, the other two are non-meaningful, right?
Sorry, which one is the instance and which one is style?
Okay, so that's the confusion. So let's do it. I'm going to transfer this. I'm going to call this the style, and I'm going to call that the content or the input, right? So this is y, and that's x, right? So I'm going to do the same analysis. So now what I have done with x, with that one, is I have removed the statistics. I have centered the image and I have removed the standard deviation. Okay. And now when I do the transformation outside of the parentheses, what I'm effectively doing is I'm copying the statistics from this image to that image. Right? So the blue distribution now is empty. But now I'm going to copy the distribution from the red channel. Right? So when I multiply this by the variance of the red channel, then whatever distribution here is going to be spread or is going to be compressed by this variance. Right? So that gives me the shape of the distribution. With the sigma of y, we established the new spread of what the channel is going to look like. And with the mu of y, we set the center. So we have effectively copied the shape of the distribution from the red channel from this image to the blue channel of that image.
Just wanted to make sure that everything here is three-dimensional, right? X is three-dimensional, mu x is three-dimensional, sigma y, everything is three-dimensional, right?
Three-dimensional as in three channels?
Yes.
Yes, but we don't care. We don't care because for the sake of the example, we have said that the other two channels that we are not analyzing are empty.
No, for this example, like in normal case, when you have color image, you can have three channels,
Yes,
right?
yes.
So all of these values are three-dimensional values, right?
But we're reducing it to one channel for the sake of the example to see how the shape of one channel can affect the shape of the receiving channel.
Just for clarity, there's two very important assumptions here. One is that the style is in the color, right? Because if it was in the blacks, that wouldn't work. This wouldn't work at all. So if you had black and white images, you would have to. I don't know exactly what would happen. It might still work. And then I think the other important detail too here is that you're in terms of the statistics, we're being a little fuzzy here when we're saying you're erasing all of the information. What you're doing is you're sort of collapsing out the relative information, right? Because once I reduce the variance to 1, then if my red channel was a lot stronger relative to some other channel, by reducing all of the different channels to 1, the relative information between challenges is actually being collapsed. You're not actually erasing information, but you're bringing it so that all of the informations are relatively equivalent.
Yes, you are correct. I refer to erasing so you have the picture of what an empty channel looks like, but you are more accurate.
Yes, I actually really like that, so think through that, but just for clarity, I just want more for the video as well.
I still have one, I'm trying to do some intuition here. So does that mean if you have a lot of variance in here and the style,
Yeah.
then your instance becomes more important?
You increase the variance of your
Why is
instance.
that? Why is that?
Because here, so this is you have a random variable here, and we have normalized the random variable, right?
Okay.
So after normalization, your variance is what, 1, right? And then every element is going to be multiplied by this variance here. So you're effectively spreading your distribution, right? And then you spread it, and then you center it by how much you translate. So shape-wise, you have a histogram that resembles. It's not exactly the same because you don't lose the information, but you have a histogram that tries to resemble this style, right? So we only are talking about color here, but imagine now that we are applying the same operation to your kernels. So we have, at some point in the synthesis, you have a brush that is very broad strokes, like, like very broad strokes, right? That kernel is going to have, these two statistics is going to have a mean and it's going to have standard deviation. But that could be shaped by the style you're trying to transfer, which is going to be maybe a stroke that is not as wide, right? And maybe it has, so that's the intuition. You have shape and color, right? If more philosophically speaking, this is how artists produce their work, right? You have colors and you have brushes, and so one thing is color. So we understand how this is kind of working with the distribution of colors, but also think of the kernels because the same operation goes here. So, all right. So that's the intuition behind the add-in operation. You are transferring the style by looking at the statistics of the image. Now, this network starts from this point. This is the previous work from the same research group. They are going to build the network that we see in this paper from this network. And this is called a progressive GAN setup. Who has seen this before?
Just want to point out, there is an older TDLS video on this.
Yes.
Go look up my YouTube channel.
So go to YouTube and check your video. Awesome. All right. So for those of us who haven't seen this before, let me tell you that the basic idea here is you start with a very simple network. You have a generator here, and then you have a decoded generator and detector. Discriminator. So you start 4 by 4, and as you progress during training, you start on the live wire, you start adding more layers. So please notice as well that every layer that you add is effectively duplicating the size of the previous kernel. Right? So you have 4, 4, then 8, 8, and then you get to the point where it's 124 by 124. All right? So the idea is you start learning, and as you progress during learning, you start dropping in more layers. So that's the key behind this setup. Now the idea, so you start with something that looks like this, and then you move to something that looks like this at some point. Now the idea is that before adding this 32 by 32 layer, what you do is you progressively add the influence of this new layer into training. So you're doing a linear interpolation here that is determined by this factor alpha. So at the beginning, alpha is 0, right? So if alpha is 0, that means that the contribution coming from here is you multiply by alpha, so this is not contributing at all. And then alpha 0, 1 minus 0 means that the contribution of this 16 by 16 is considering completely. And then if you put alpha 0.2, then you have 0.2 contribution of 32 by 32, and then 0.8 contribution of 16 by 16. And at some point, alpha is going to be 1. And when it's 1, then you have a full contribution of 32 by 32, and a 0 contribution of 16 here. So this is kind of like a residual architecture that changes over time to the point where you just have 2 consecutive layers. So it's kind of smoothing out the transition between an architecture that has 1 layer to an architecture that has now 2 layers. And you keep repeating the process until you get to this kind of structure. So this is what is going on with the setup. We haven't done anything in particular other than using the previous work at this point. Now we're going to zoom in into these two blocks. So say that at some point during training we have 4x4, which is this block here, 4x4. And then you have this block here, 8x8, which is this block here, 8x8. And we're looking what is going on inside. So here we have our code. There's some normalization at the beginning. We don't really care much about this. And then you have this block. Okay? And then you have this block here. So up to this point, it looks like it's a simple convolutional network. You have convolutions, you have an upsampling operation, and that's it. There is nothing fancy about the architecture when you zoom in. Now the first thing that they do is they're going to replace this upsample. So in the original paper, they used the nearest neighbor upsampling. So you have a grid of n by n, and now you have a grid of 2n by 2n, and then you're going to determine what goes into the empty slot in that 2n by 2n grid by looking at the nearest neighbor. So instead of doing that, they are doing a proper bilinear interpolation. They do that for the, if we go back here, they do bilinear upsampling here, and then they're going to do bilinear downsampling here. So that's the first thing that they fix. Up to this point, nothing fancy. All right? You wouldn't expect big improvements just by changing the way you do the interpolation. Maybe the strokes are going to look smoother than when you do nearest neighbors. That's all you get.
Could you go to the previous slide? Could you tell us how the training process works? You start training the model with 4x4,
yeah.
Finish, then switch to 8x8?
No, you have like time points during training where you start dropping in layers.
Like you would train 4x4, and then once it's primed, essentially, then you start incrementing that alpha value after introducing the 8x8 layers to smoothly transition into that, and then repeating that process. Yeah. So like once the 8x8 layer is in there, they would continue to train that until it is like it had reached after a certain number of iterations, and then they would start ramping up for the next rotation.
So you can think of it as being like the distinct phases, but they don't really, it's not really, you don't really gain anything by thinking that they actually stopped training and then they started then. And it is actually done online, but it's basically step counting.
We have some discussion points around this actually later. So.
All right. Okay, the second step, so we changed the subsampling layer. The second step here is they introduce the idea of a mapping network. So this is the first change here. It's a fully connected structure. It's a multi-layer perceptron. All right? And then after doing that, is you're going to add your word here, your latent code in W. You're going to inject that code at several stages in your network. And now we see this add-in operation. So let me break this down. So we start here with a code in latent space Z. For practical purposes, this is an image. Right? You take a picture, and then that's your Z here. And then here, what you're doing is you're obtaining your word. This is an encoding of that image in what you call the latent space W. All right? And then here, what you're going to do is you're going to apply an affine transform. And this affine transform is actually the parameters of that affine transform participate in backpropagation. So those are learned. So basically, how much this word that we're going to call the style affect your network is going to be modulated by the parameters of that affine transform. And then you have the add-in operation that we know that doesn't participate in backpropagation. All right?
What was the input to
here?
Yeah.
An image. An image.
An image. So why is it latent then?
I don't think it actually is an image. So this was a point of confusion that we were discussing a bit. I suspect it actually, so it represents an image, but I think it is just a random vector.
Okay.
This is a generator.
It is like a generator, yeah.
So it's an encoder.
So the confusing part is that they talk about things like source images and stuff like this. And the paper is itself slightly confusing on this point, and I was confused myself. At certain points, I thought the constant thing was the image, and then because they're talking about it in terms of style transfer. Normally in style transfer, you do actually have an image, but as far as I can tell, like I don't know, correct me. Like, I think that actually is just a 512-bit vector, or a 512 vector. But we can discuss it maybe a bit more.
I think it's an image.
Okay,
So on the results, but as you said, it's kind of confusing.
It is. The paper isn't very clear on this point.
But I did go through the results, and I'm going to show you the results, and you guys can tell me what you think.
Yeah.
But what I understand is that it is an image. And this explanation is going to make sense if it is an image.
Yeah.
So,
Well, I believe it's because it's sampled from a distribution that at some point will look like the image.
No, that's not. I mean, it's.
So I propose that we revisit this point because
we're just going to argue.
we're going to talk about style mixing.
Yeah.
And when we talk about style mixing, then that probably be illustrative.
There's also no code released right now. This is one also a downside of the fast track. When you click the code thing, it takes you to a Google Doc that says sometime there will be code.
Can you go back to the previous slide? Because in the previous slide, no, actually
It makes
one
more
more.
sense as an image.
Yeah, this one too, but your input there for the generator is latent space, is a latent vector.
Yeah.
So that's kind of, usually for the generator you have a random thing, or you can use a real image for the generator. But
you'll see. It's this network is very weird though. So
this is like when you go to hell, and there is this sign that says leave your hope behind you. But I know what that is. So we're walking into that right now. We need to lose the assumptions and the concepts that we have about
really weird.
because this is intuitive. We're trying to make this fit into the idea that we have of a GAN. And if we leave that behind, this probably makes better sense.
It does make sense.
So let's assume for one moment that I'm right. Okay, I don't know if I am, but let's assume for the sake of the example that I am.
You trust.
Right?
To be honest with you, it will make more sense if we assume that.
If you trust me, then it will make sense. I may be wrong, but well, let's see how it goes. So here, so we have some sort of input here that I'm calling an image. All right, and here what we have is a representation of that input in a latent space that we call W, and this is our style. Right, so we're going to take the style from our image and we're going to inject it into this synthesis network. All right, at different stages, so different level of spatial resolution. You start, for instance, here in the first block. This is 4x4. You would imagine that whatever styles we inject into the coarser granularity are going to affect the entirety of your image. Later on, we're going to see that styles such as the skin color or the pose of the head fall into this category. All right? If you start injecting styles later on, as we do the synthesis, we know that here we have more granularity, more spatial granularity. And you could think of the eye color, or you can think of earrings, things that are more fine. So this style could be visible at these levels. Now, something that is also a discussion point is the fact that here we have a constant.
A trainable constant.
A constant. So you would imagine that this is your random variable, but they're saying, no, it's not a random variable. It's a constant. So I read the paper and I'm scratching my head. This is not what I understood about GANs. So why are you jerking me around? Okay. So this is my.
It's a fixed random value. Yeah, that's learnable.
This is my rationalization of this situation.
That actually makes sense. Yeah.
So we know that we need to use an ADA-in. Okay. So we have an ADA-in here, and that ADA-in needs something, right? We need to transfer the style onto something, and we have nothing. We have that empty canvas. We have that block of cement that is unsculpted. All right. So that's this constant here. Imagine freaking big block of cold cement. That's it.
So every value is this.
No, every value is not the same. It is learnable because you can change the values.
So, an interesting observation. So, like, I've tried this with the time series. What I noticed with that constant tensor, like it visualizes in tensor board, across millions of iterations, like training steps, that constant tensor didn't change even though it was learnable, with the exception of like maybe within a small percentage, like less than 1% overall change in the tensor. And I think that was more likely due to floating point error than anything.
Yeah.
Okay.
Now think of learnable parameters. And you start from the top here. We know that the ADA doesn't have any learnable to it. The first layer where you have something learnable that is affected by backpropagation is that first convolution, right? And now assume for 1 second, without losing generality, that constant is a random vector that has zero mean and 1 standard deviation, right? So hang on. If you do that and you go through the ADA-in, we know that when we subtract the mean, we're subtracting 0, because I just said that was the distribution. And if you have a standard deviation of 1, you're dividing by 1, so it's not doing anything, right? So effectively, if that is the situation, then the output of the ADA-in is going to be what? What is going to be something that looks like this, a style block.
Yeah, a block of nothing that has a style.
Well, so I was
Yes.
I was just going to point out, so you're saying there's a constant over there, but it looks like there's a noise that has been added to the constant.
This?
It's not really.
I can talk about that.
But they do it with and
Nice.
without the noise.
So yeah, so the way I'm doing this, I'm going part by part because there are so many moving parts here.
I'm sorry to jump.
And you look at the whole thing, it's like, how the fuck is it working, right?
Sorry to move.
So what I'm doing is I'm doing it by parts. So yeah, so you have this, and then we have a block that is nothing, and we're just adding. We need an anchor for this first add-in operation, right?
Is that constant in reference, in inference? Sorry, as compared to
Yes.
It's
learning.
constant.
It's just always a set of numbers.
From the beginning of
So
the
you're
universe.
saying there is some learning.
It's the unsculpted clay from which all things spring forth.
I mean, you really have to come up with that.
Primordial.
That's
Okay, hell and then clay. We're becoming
It's a
very
constant.
religious here. So
It's a constant.
okay, so
a
there
constant.
is okay. My question is,
Yes.
then there is no difference for that constant in terms of training and inference.
Well, there is okay. So this is what I understand. So if you change this by something else, then that effectively is going to change the distribution of your weights in the convolutional layers, right? You start from something that has, I don't know, that has one element here that is very large, then that particular weight, you simplify things, then it's going to be different. But at the end of the day, it's not really going to affect the training process.
in other words, you can't randomly sub that constant out with another constant that even has the same mean and variance because the network was trained with that specific
Yeah.
clay.
It's your
Anchor to it.
digital signature, your PGP, your
I guess it will make more sense if you carry
No.
on.
No. You just have to roll with it. That makes
We need another beer here. please.
Another way of interpreting it, and we weren't totally sold on this, but you could also think of it as just a very weird bias,
Yeah.
right? Because remember what your bias values do. They just start with your base signal, and they can vary across a network layer, right? But weirdly, we just have a bias. And I mean, this kind of makes sense in the sense of a raw clay, or if you want to use that metaphor, just because you need to have something that you want to generate your images on, and you don't really want a whole bunch of zeros. Because if you're doing this weird style thing, right, if you're thinking about things in terms of their mean and variance, then you want predictability in terms of that mean and variance, which, because it's a Gaussian distribution, that raw clay has the properties that you want.
Let's say that we have a bunch of zeros, right? So the mean of bag of zeros is 0, and the standard deviation is 0. So when you do ADA, you have 0 over 0, and it doesn't work because it goes to infinite.
Yes.
You need to have something,
But it's not undefined.
right? Can I move on, please?
I guess
We have
my question was, so it's a very simple question. During inference, does that constant ever change? Yes or no?
It's a constant.
During training, does that constant ever change?
No, it's a constant.
Okay.
So what is learnable?
Yeah, what's learnable?
Yeah. What is learnable?
What is learnable? Well, whatever.
It's-
If you look at the structure of the network, then you know that all of this is learnable, that these affine transforms are learnable, that the convolutions are learnable, that the noise effect that you have here is learnable. This is not. This is not.
Okay.
You can make them learnable, but it doesn't learn, like no gradient.
Oh, so it's not learnable, you're just adding a variant noise to it.
I have an issue with calling it noise because in my head noise is something that is like chain, right?
Fair enough.
So
Signal.
bias probably would be a better word for it.
For your B?
For
No,
this.
the constant.
For the
We're still
constant.
only talking about the constant.
So the next slide is about B.
Okay.
Maybe
So-
let's just keep going.
Yeah.
So B, unlike the effect of the style, so you know that here this style goes through the align operation and it affects the entirety of your activation map. So remember we talked about the color channels and we talked about the different kernels. So the style transfer occurs to the entirety of the kernel. Okay, so it's a systematic effect. Here we have noise, stochastic noise that is added pixel by pixel. Okay, so this gave us a little variation, but you wouldn't see a systematic effect as the effect you have with the align operation. So this is important to keep in mind. So I think I already kind of explained this. The idea is that
Okay, I had to cut you, but could you go back to the previous slide?
Yeah.
It's literally calling noise.
yes,
You
this-
just told me that.
That is-
no, sorry, I was referring to the
The
constant.
constant is not.
Oh,
Yeah,
I was
because we're
referring to
talking
B.
about the constant, and
No, no,
you
I
said
was
no, I
referring
said
to
no,
B.
it's the constant, but we're talking about the constant.
Fair, that's fair.
Yeah. So
I was confused because
I was confused too, but I know that we are in the middle. Yes?
Yes,
Okay. So this is basically to re-emphasize something that I've been going over and over and over. This is how you transfer the style. You have here a convolution, and then this convolution you have a set of activation maps that somehow are going to be affected by this style through the align operation. So this style is going to change the relative importance of your features that you are getting from this, the output of this convolution. Okay, so I'm just basically saying the same I said before. And the effect of the noise, because it's not applied consistently through, it's not an operation that occupies the entirety of your kernel, you see that the network learns how to use this input. So the parameters that you learn here affect features such as hair. You have a small variation caused by the stochastic noise that you learn. This
So it's almost invisible, unfortunately, because of the lighting and stuff, but
Can we flick the lights like just for?
yeah, just maybe turn them off for a second.
Oh,
Well-
no, it's okay.
Wrong way. There you go.
Yeah. So when the network learns, then that input that is changing from pixel to pixel, you know that you need consistency, right? So you have your generator generating a beautiful image that looks like a human. And then you need to learn the parameters of that noise that is affecting pixel by pixel. So through the regularization of your loss function, you know that where's the effect that you see, the behavior that you see, is that the noise is effectively changing things that are not systemic. Right? So you see a stochastic variation in things like the hair. And this is kind of like an emergent behavior because it's not, it is designed for it, but it's difficult to get our head around around the whole situation, because this is one of the first time we're looking at how to structure a generator.
So,
Okay.
just to add to this, remember the key thing here is that when we're operating from the latent space, or even what we're expecting from the clay, right? The constant, the constant values, is that information is not being used to encode this variation. It's somehow being used to encode the fact that it is hair, but not exactly the fine-grained detail of what the hair is, right? Or exactly what the distribution of the hair is. And the other thing that I wanted to highlight here as well is that if you remember back to StyleGAN, I don't remember if they do it in progressive GAN, but even some other networks that were designed to operate on images, you often saw them embedding noise at higher layers in the network because you wanted to increase the variation or give the network variation so that so that whatever your latent information is, whatever the network is learning, is not having to produce noise from that learning, right?
Yeah.
So how does that constant relate to this one?
What constant?
So you just said that.
What I'm saying is
Yeah,
that
the
your
constant-
base signal or your style signal is not being used to actually produce noise. That's all I'm saying.
This is noise and high-level features at this
So
point.
this is what they show us in the video. If you remove the noise input, what you're going to see is that the strokes that correspond to hair and to wrinkles and to small variations in the background disappear. Right? Because those kernels are not learned, they are not represented by the convolutions that you have, nor those are present in the style that you're trying to copy.
If you remove the noise, you're saying.
There's noise being added on the side there.
So this is a artifact of the noise getting added.
It's not an artifact, it's a byproduct of having that noise input.
Or a feature of that noise.
That's what I meant.
Yeah.
Yes, good.
Yeah.
Let's go.
So is it correct to say that the network automatically learns to only add noise to the kind of the
Yes.
finer resolution blocks of the network?
Yeah, so I have a good explanation for that. So imagine that you have your set of strokes, or you start cadence and you start painting, right? And then you have something that looks like a portrait. And then you're going to compare that with an actual image, right? So you are encoding everything that you know, all the colors and all the brushes and all the strokes, through the style, and then you get to the point where you produce something that is very even looking and has a lot of homogeneous regions. And now you're going to improve your learning by propagation, but the only other variable that you have to learn is those weights that you receive from the stochastic noise input. So the only thing left to do is this. So when you use those weights here to improve the result, then you end up learning things that are not represented at all by your kernels, such as wrinkles, hair, and small elements in the background.
One thing to notice here, though, too, is that you have noise being injected at every layer, essentially, every block. And so the coarser layers, like the 4x4s and 8x8s, are going to be adding stochastic variation to coarse features. Things like, because we're talking about faces here, things like the overall shape of the face, there'll be variation there. Yeah.
But the
and so
variation will be more visible in the finer.
So as you go to higher resolutions, the noise is going to then affect finer details.
I would bet, we can do the code review, and I'm going to bet $10 that when you look at the distribution of weights in this layer, the distribution of those gradients is going to be minimal. Because at these layers, most of the contribution is coming from the style.
That makes sense. That makes
right?
sense.
One other thing to note too is the noise, the amount of noise that's applied is there's a learnable parameter that controls how much noise actually is injected. So the generator gets to learn on a per channel basis how much noise is appropriate for that.
So eventually it learns to add more noise to the finer kind of details of the...
Add is weird in this case. It's more like let more noise through.
Okay.
For people, so what's the shape of B?
I don't know.
Okay.
That's what I'm curious.
So it would be the same as the output there, because it's essentially just like it's an additive noise. It's like the layer plus the noise, and the noise has already been mapped.
But I thought it's the
it has been
noise.
scaled.
Noise multiplied by B.
Well, actually,
Something like that.
I assumed it was the same shape as the image.
B is, my understanding is that B is a dense layer. Actually, I would have to check that if B is a dense layer or if it's just a scale
on
parameter.
page 5 of the paper, figure 4, they look at standard deviation. So those pixels that show you where you actually have information. That's the shape of the noise. So wrinkles also in the clothing, and for the most part the hair. That's what you get by adding that. And in the video, you look at that when they remove the noise, it looks like a portrait, like it's been painted. So it's very interesting.
What is so because of the
So this noise is like a simple Gaussian noise.
Yeah, it looks like it. It looks like it. Yeah.
Okay, so if it's a simple Gaussian noise, the learnable parameter will be mean and STD. So is there a way to get around of this effects, these artifacts? Because if we learn to get rid of higher frequencies, or learn how to keep those higher frequencies, which is here, for example, higher frequency, right? So we can actually learn this, but I didn't get why you have those weird part of the image
So
in here, instead of learn that.
Yes, so think of what type of kernel would you need to be able to represent that? So at some point, you have a 124 by 124, right? You get to that level of resolution. So you wanted to get to the pixel neighborhood style where you have very small variation. Maybe you cannot learn that with a kernel. Maybe the best way of doing it is just through random stochastic variation and let the network apply that randomly. Because remember that this effect is by pixel. So maybe it makes sense to do it that way, rather than through a kernel.
I mean, remember, there's like, it's very, the distinction here between what's learnable and not learnable is very subtle, right? Like, so there is noise being injected into the system, right? And the network is able, because there's a convolution almost always following, or at least an upsample, there will always be a convolution following when noise is added into the system, right? So what that convolution can do then is it can basically say, okay, well, yeah, or yes, we've added this noise in, but we're going to gate a certain amount of how much that noise is actually going to be affected by it. So the noise is still always learnable in a way because its impact as the layers
learning.
Yeah,
will be indirect learning from the convolution kernels.
Right.
But not from not from the parameters of the Gaussian distribution.
No,
the Gaussian noise.
Well, I mean, you'd expect some association, but like, I think.
Are you saying that the regulation of the noise is learnable, or the noise is?
What I'm saying is that the impact of the noise, the scale of the noise is learnable, we believe. But what I'm saying is the impact of the noise is also learnable because downstream from that, once the noise has been injected into the system, you do have trainable layers always, right?
But B is constant.
No, B is learnable.
It's not that.
So it has weight.
So I just want to add something. So this is my understanding of GANs. It's like when you inject noise to the GANs, right? So the weights of the GANs network, they adjust themselves to, get the noise and produce what it wants to produce. So I think that's what is happening here. You're just injecting noise at different points, but the weights that are learned in the network, the weights kind of understand like how to respect that noise.
So this is the way I understand it. So that B is the gate, right? So how much of whatever noise I'm going to accept on each layer, right? My $10 bet is that weight is going to be really small in the first layers because you learn most of what you need from your styles. And you're going to see a higher B, and we can test that when we do the code review, that you have more influence of the noise in the upper layers. So again, imagine that you have the portrait and a real image, and you find your loss, right? But you cannot encode anymore in the kernels because that's how far you go with learning. Your kernels are just fine. So where are you going to take to make your portrait look more natural, to get those wrinkles, to get those crevices on the clothes, and those hairs? Then the only option is to allow the noise more on the upper layers.
So,
make sense?
quick question before, because I know it's just a detailed question. Do you have the picture in here where they show, not that one, the one where they
this one?
Yeah. It would be worth everybody, maybe we'll hand this around during the break, but it would be worth looking at this picture here on the square with the child and the man, because what picture, I know I can't show.
Did you say the figure number?
The figure number is figure 5.
Why don't we just pull
I
up
see.
like this is a computer, right?
It's your computer. I mean, yes, we could do it that way as well. I'm fine with that as well, but the point is that the figures show what happens when you're injecting noise at all, not that one. No,
Next picture.
To the right, to the right, yeah. So yeah, this is the picture. Yeah.
This one?
Yeah. So the top left one is noise at all layers. The top right one, I believe, is noise at no layers. Is that right?
At different layers. So A is at all layers, B is no noise.
Yes.
So here, let's look at this one. So no noise. This looks more like a portrait.
That's what B is on the right side.
Continuous is something that you have encoded with your kernels. That's the most you can do with kernels.
Right.
And
Well,
pixel,
that's subtle.
$10.
No, anyway, just go ahead.
Learnable, how are you changing it? How are they changing it?
I think we're like going in circles.
We don't know. We don't know how they're changing because they don't say, unfortunately. I would expect mean invariance.
So,
Here, so maybe this example. You see how smooth looks on one side and how more realistic you have on the other side?
On the left here has noise.
In this case, it's not, well, you see the hair there, but also you can capture, light reflection on a surface. You capture that better with stochastic noise. And so you encode it on this side of the network rather than on the...
So all the B's are now are injecting noise. And then what the other images show is that if you only inject noise at the low-level features, you get variation in large-scale structure. And if you only inject noise on the high-scale features, you get variation in very high-scale structure, but no variation in low-scale structure. So it's exactly what you would expect to find, but you'll notice that when the noise is being added, it's not arbitrary noise, it's structured noise, right? So you're getting high-frequency detail in curls on the hair, for example.
Yeah, but why is it a structure?
Because you have all the convolutions.
You control where, right? Where you are using it. So that's the key. Like, so I didn't realize that this was actually a very important starting point. When I came to today, I said, we're going to emphasize ADA-IN and how ADA-IN works. But now through discussion, it's clear that understanding this part is also very, very relevant. So we have our image.
Okay.
And then we get that code here for that image. This image is the style that we're going to use.
Latent in that example is the child.
Sorry, what?
So that latent Z in that your particular example, the child photo. So that's the.
So
what in that example, what is latent Z?
An image.
An image of.
An image that you're going to use to copy styles to something else.
Like the child's photo.
That's your input here.
Okay, and then the details are added with the.
When we see the results, it may make sense. Not guaranteed, but I think it could make sense.
Okay, sorry, just try to keep it short because you're good, quick summary.
No, I know exactly.
So we start here with an image. Here we encode it. We obtain a latent code in W space. And then we're going to input that style that we're calling, the W is the style. And we're going to inject it at different levels in our synthesis network. We start here with a constant that serves as the anchor of the first ADA-IN operation. And then here, what we're going to do is we're going to start transferring the style at different resolutions. When we effectively what we're doing is the shape of these kernels at each point are going to be influenced by the style, and we're encoding stochastic variation through this noise channel. Okay? And then, learnable. All of this is learnable. Convolutions are learnable. This gate is learnable. ADA-IN is not learnable. ADA-IN, the fact that it's not learnable is a big difference compared to batch normalization and instant normalization.
One small detail to that diagram that might not be clear, and that is that A and all of the A's and all of the B's are independent. They're not the same.
True. So that's really a good observation. So what that means is that the effect of the style, of the particular style, is going to be different. So here could be different from here. All of those are A because it's the same operation. But the learnable parameters are independent.
So were they injecting A into each layer twice?
Why twice?
Before.
Oh, here.
Yeah.
Okay, because the way they're doing is before and after the convolution.
We don't know why.
Hi everybody, welcome to TDLS. I'm Lindsay, I'm one of the members of the steering committee. If you liked the video you just saw, subscribe to our YouTube channel and you'll be the first to find out about every video we put out.